So we're going to talk about limits, and we're going to start with the intuitive concept of what we're really doing when we talk about limit. And I'm going to use this example as a motivating example to give us some idea of where this is going. So first thing I'm going to do, I'm going to graph it, right? So blah, 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 blah. So what am I going to do? I'm going to, because it's a rational function, let's see what's in the bottom. I need to do this, and I figure out about asymptotes and stuff. Okay, and now I see something a little bit strange, right? I can cancel these guys out, or I want to cancel these guys out, but I have to be a little bit careful, right? This goes back to what we were talking about, okay, domain, whatever. It only makes sense to cancel the top and the bottom when I'm away from the point at x equals 1. Because at x equals 1, I have this thing where it's 0 over 0, and I don't know what that is, right? It's just not part of the domain. We don't know what it is. It's not defined there. So really, what this function looks like is like this. As long as I'm not at x equals 1, I can cancel these things out because it's always going to be the same number. So the function looks like 1 over x minus 3 for everything that's not 1. And then at x equals 1, I don't know what it is, so I have to write undefined. Okay? So what does it really tell you? Okay, now I go ahead and I graph this thing. This would be here, say, here's 1, 2, 3. Everywhere away from the point at x equals 1, it's just behaving like this 1 over x minus 3, right? So if I put in 0, I'm going to get negative 1/3. If I could put in 1 for here, I'd get negative 2/3, but I can't put in 1. It's not defined there. I've got to put in that open circle. Remember, we've all seen examples like this before. If I put in 2, wait. Right, negative 1/3. Okay, so fine. Now we're getting like a little bit bigger, right? So I've got negative 1. And as I go closer and closer to 3, I'm going to hit that asymptote that I already drew there immediately at x equals 3, because I know if I have x minus 3 in the bottom like that, it's going to be an asymptote. So I can see what's going on with this curve. Yeah, maybe I should have drawn a little bit more of that. And then over here, it's going to do this. Okay? So that's what my curve looks like. The reason I wanted to pick something like this is so that you can see this business with the whole and the way it comes from the algebra here. Okay? If you just go to Desmos, say, or GeoGebra, or even your handheld calculator, and you put this in, more than likely, you're going to get this. You're not going to get any hole there because the calculator doesn't necessarily put every point in there, right? So it doesn't necessarily know. So you have to sort of know from the algebra, we know more than the calculator knows, right? We know more than the computer does. So this is what this example looks like. If I look at the natural domain of this function, I have to throw out the point at 3 because here, of course, I have an asymptote. But I also have to throw out the point at 1 because if I put 1 in here, I'm going to get 0 over 0, and I don't know what 0 over 0 means, right? In this case, it kind of means it kind of means yeah, 1/2, right? Negative 1/2. Which doesn't quite look right, but we have it. So you get the idea. What do I really want to talk about, though, and why am I picking this, is this whole curve, just like the way your calculator or the computer doesn't necessarily see that that hole is there, if I'm pretty close to the hole, I'm still going towards that point, right? That point would be, that missing point, I put in 1 here, right? So that would be, right, -1/2. So it's not drawn that well, but okay, we'll pretend it's there. But your -1/2 is where that hole is. And as I go along this curve, either way, I'm tending towards that hole. If I make my picture bigger and bigger and bigger, right, I'm still going to end up with something that looks like that. And with that hole at the point where x equals 1 and y equals -1/2. Okay? So that's kind of what we mean when we're talking about the concept of a limit. We're talking about, let's look on the y-coordinate and see where the function is going. It doesn't really matter what the function is actually doing at that time. It just matters where the curve is naturally going to. Right? So, for example, all right, let me just write that down. From both sides, and we'll call it f of x. Let's call this f of x. The y value tends to -1/2 even though there's a hole. And so the way I would write that is the limit, and I want to write LIM, I put x going to the point that we're interested in, which is 1, and I put the name of the function, and I'm going to say that the limit there is -1/2. Okay, so that's what I mean by that. So this is the y value, this is the x value, and we're talking about what happens with the function. Okay, and it's going to be the same thing whether there's a value there or not. So for example, at 4, right, what's this point? F of 4, okay, obviously I didn't draw that well because f of 4 is 1. So let me it go down steeper because 1 would be like right here. Okay. I just didn't draw it going down steep enough. All right. So I can do the same thing over here. I can talk about how the function is moving. That point actually is defined there as a nice continuous function. Limit as x goes to 4 of f of x. If I look at the graph, okay, in both ways, it's going to that point. So we would put limit of f of x equals 1. Now let me switch it up a second. Let's say, I could fill in this hole, right? It's undefined here. So I could define it. Now it's going to be a different function. I'm going to call it g. And I'm going to change a different function. I'm going to give it some definition. I could just fill in the hole and call it -1/2. Maybe I want to switch it up though. Maybe I want to make it 2. If it's defined to be 2 there, that means I can now draw a point here on my piecewise defined function, and I have that point just out there willy-nilly. Fine. So now, if I look at the function g, I can put in g of 1, and clearly the value is 2 because that's where I stuck my little point. But if I look at the behavior of everything else near 1, it's still tending towards that empty circle. So if I'm to ask what the limit is as x goes to 1, I'm still going to get that value of -1/2 because it's like this guy is off, it's an isolated point off wherever, but the function around that point, it's still doing the same thing. Okay? So that's kind of the idea of the limit. And let me kind of give a sort of a definition here, sort of a kind of an intuitive definition. So you got x is near the number a. So this actually means near everywhere but at the point a, meaning that f is defined in some open interval around a. Let me say number x equals a. It doesn't necessarily have to be defined at a, but let me just write that. In some open interval containing x equals a. Then we say the limit of f of x as x approaches a is L, which is a lot to say, right? But in symbols, which is the way we'll write it, we write it the way I wrote it on the previous thing as x goes to a of f of x equals L. So what does this mean? It means that if we take values in x very close to a, then the values in f of x or y are getting very close to L. Okay, so hopefully you can see that. And so we had three sort of pictures that we looked at on our example, on our motivating example, where that limit existed. So let me just put these up here. Our first example, this is A. No, doesn't really matter. I'll just do it like this, right? With something like this. So this was the value of A, and this was the value of L. Okay, so in this example, I have to have space for 3 of them. There's an open circle, there's no closed circle, but you can see that the function basically wants to go through that point almost. It's just not there for some reason. The second example we had was something like this. They're not all entirely the same because I'm freehanding it, so sorry. Where here's A, and there's L, and the function value is, in fact, L at the point A. So it's nice and close it together. And the third possibility we had, which is the last example I did, was something where we had this business. but the function value was somewhere else. Okay. So in all of these three pictures, though, if I look at what I'm asking in this very end of the definition, I'm saying, let's look up really, really close in this. If I zoom into this picture, look very, very close, the y values are getting very, very close to L. That's true regardless of what the value of f at L is, if it even is there. So that's the intuitive definition part. Now, in the next video, we'll look at some cases where the limit doesn't exist.